Mr. Heffron here, and here's a video on graphing motion in physics. So we're going to be using different kinds of graphs: position time graph, velocity time graph, acceleration time graph, and of course the equations of motion. Okay, so for kinematics graphs, there are three main types of graphs which used to depict the motion of an object. So we have our position time graphs, which are indicated here with a d versus t plot. Velocity time plots, v versus t, and acceleration versus time plots. So here's an example one, position time plot. So Jack and Jill are north of the well, and they accelerate north for some time interval. Use the graph below to determine their position, displacement, velocity, and acceleration. So here we can see they started off 10 meters north of the well. We'll assume the well is our reference point at 0, and they started north of it. So moving up the graph here would be north, going below, which isn't shown, would be south. And at 0 seconds, they're 10 meters north of the well. All right. Where did they end up? At 10 seconds down here, they finished off at 60 meters. So they went from 10 meters, their initial position, to 60 meters, their final position, both north of the well. So their displacement is 50 meters north. Okay. Also, the graph has a flat slope of 0 meters per second here at the bottom. So here, before they start moving, the slope of the graph is 0. They're not moving. They have no velocity at this point in time. And then they get faster and faster and faster and faster. You can see it's getting steeper and steeper, the slope of the curve here. Eventually, at 10 seconds, we can draw a tangent line. So a tangent line just touches the curve. It doesn't go through the curve. And if we look very carefully on this tangent line, it goes from 8.3 seconds to 11 seconds. It goes from 38 meters up to 65 meters. And if we find the slope of the tangent line, that should tell us our instantaneous velocity. So, so top subtract bottom, 65 subtract 38 meters. That works out to be 27 meters. And then right subtract left, 11 subtract 8.3 seconds. That's 2.7 seconds. So you get 27 meters divided by 2.7 seconds. They have a final instantaneous velocity of 10 meters per second. So you start off at flat lined, 0, all the way to a steep line right here of 10 meters per second. Okay, we can also use some equations of motion. Just look at the data here. So we know the displacement. They're going from 10 meters to 60 meters. That's a 50 meter displacement. And we know that took 10 seconds. We also know that they started off at 0 meters per second. So the VI is 0. So when we fill in the formula, displacement is initial velocity times time, plus acceleration times time squared over 2. We have the 50 meter displacement, 0 meters per second for the velocity, time of 10 seconds, and time 10 seconds again. And when we work this out, we get an acceleration, an average acceleration of 1 meter per second squared. We can also use a formula, now that we know the acceleration is 1 meters per second squared, to find the final velocity. So our final velocity, this steep line right here, subtract 0 meters per second, our initial velocity right here, is equal to 1 meters per second squared from our previous slide, times 10 seconds. And we get a final velocity of 10 meters per second, which is the same answer as the slope of our tangent line from a few slides before. So now we know the whole story for Jack and Jill. They started at 10 meters per second north of the well, accelerated north at 1 meters per second squared from rest. They accelerated for 10 seconds and ended up 50 meters north of where they started at a final position of 60 meters north of the well. They finished with a final velocity of 10 meters per second north. We could now draw a diagram of the scenario based on the DT plot. And here we go. So here's the well, and we've rotated the compass here, so north is on the right side of the paper, or the slide. So here they are, Jack and Jill are starting off 10 meters north of the well. They accelerate at 1 meters per second squared, and 10 seconds later, they're running at 10 meters per second over here at a final position of 60 meters. Now we can actually make some graphs from that, maybe. So, first Jack and Jill started at 10 meters south. Example 2. So, we're going to make a velocity time plot. So first Jack and Jill start 10 meters south of the well, and they're at rest for 5 seconds. So what would that look like? So if you're 10 meters south, or minus 10, and you don't move, you're going to have a flat line. Of course, you're not moving, so 0 is your velocity, and you're not changing your velocity, so your acceleration is also 0. Okay. Another example. Second, Jack and Jill accelerate at 2 meters per second north for 4 seconds. Now I use the equations to find the velocity, final velocity, the displacement, and the final position. So, if they're going to accelerate at 2 meters per second squared for 4 seconds, using this equation right here, we'll find they move 16 meters. We'll find they end up with a final velocity of 8 meters per second. And their final position will be 6 meters to the north. How will this look as a graph? So, they initially weren't moving for a while, and then they accelerated at 2 meters per second squared, and ended up at 6 meters north. The velocity, they were not moving for a while, and then they accelerated, and their speed increased at 2 meters per second for every second. And as far as acceleration goes, they had no acceleration, then they had an acceleration of 2 meters per second squared. Okay, so velocity time plot. Now we can make a velocity graph based on the information we have. So, third, Jack and Jill maintain a constant velocity of 8 meters per second north for 6 seconds. So what would that look like? So they're going to change location by 48 meters and end up at a location of 54 meters. So here we go. So they initially weren't moving, then they accelerated, and then they maintained a constant velocity, which is a nice straight sloped line, and ended up way over here at the final location. As far as the velocity goes, they start off at rest, they increase their velocity, and then they maintain a velocity of 8 meters per second. So for their acceleration, they had no acceleration. They accelerated for a little while, and then they went back to no acceleration as they maintained their velocity. So in summary, the equations of motion can be used to make graphs. So these graphs include position time plots, velocity time plots, and acceleration time plots. And these graphs can be used to tell a story. So like pictures, a good motion plot is worth 1,000 words. So equations of motion do work in unison with the different kinds of plots. I hope this has been informative.